Good day, I'm Norman Wildberger. We're on our way to critiquing real numbers as Cauchy sequences of rational numbers. Before we do that, we have to explain what a Cauchy sequence is, and before we do that, we properly need to discuss more this rather sensitive topic of what a sequence is, especially what an infinite sequence is. That's what we're going to be tackling today. In our last video, we talked about regular sequences or finite sequences. Today we're going to see, can we make this jump from the finite to the infinite? Well, it turns out that we have to take great care when we try to move in this direction. These are not just two different sides of the same coin. There's a vast gap, vast chasm between the finite and the so-called infinite. In fact, it's not at all clear what we mean when we talk about things which are infinite. That's part of the problem. All right, so to illustrate things, what we're going to talk today about are so-called infinite sequences that come from Neil Sloan's online encyclopedia of integer sequences. So last time we talked about finite sequence, like say the sequence 1, 3, 5, 7, stop, or the sequence 2, 4, 6, 8, and so on up to 1146. This is not entirely completely specified here because I haven't told you what these three dots mean. But if I explain it in words and say, well, it's all the rest of the even numbers from 8 up to this number here, then you are in a position to recover the sequence with some work. So these are finite sequences, and we feel that we have control over what they are. Today we're going to talk about the big step to these so-called infinite sequences, which arise in practice in many, many different ways and fashions. And there's so much to be investigated here, as is made clear by Sloan's wonderful online encyclopedia. We're going to look at a few entries from his collection, in particular A000040, which is this sequence here, which is the sequence of prime numbers. And another one, probably less familiar to most of you, A000108, which is this particular sequence. If you're a combinatorialist, you may recognize it, but otherwise it may appear a little bit unfamiliar. It's a rather remarkable and important sequence. So we're going to be able to talk a little bit about general sequences in the context of these kinds of simple examples. So I'm trying to raise some of the issues when we try to be more precise about what an infinite sequence really means. Of course, we in fact began this series of lectures with an even more elementary and more fundamental sequence, which was the natural number sequence. And we are using the word sequence here in an informal way. We have not yet defined what we mean by an infinite sequence. And in fact, it's going to be very problematic for us to do that, as we'll see. Nevertheless, we talked about this pattern, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and so on. And a little while later, with some more sophistication, we rewrote that in the Hindu-Arabic form as more familiar 1, 2, 3, 4, 5, 6, and so on. So there's a question here. The question is, does this sequence really go on forever? Or is this really an infinite sequence? That's not such a facile question as it might appear. It's clear that when the numbers are small or reasonably small, we can always add one and get the next one. But as the numbers get bigger and bigger and bigger, then theoretically they are going to start getting so big that they overwhelm our memory supplies, that they overwhelm perhaps the size of the solar system or the size of the galaxy or maybe even the size of the universe. At which point it becomes perhaps problematic about whether this sequence actually does go on forever or not. In fact, it's not even clear what that means, to go on forever. So these questions are seemingly related to physical or metaphysical questions, cosmological questions, such as, does time go on forever? Is the universe finite? Will mankind live forever? And there are other sort of related questions. I mean, if our universe is finite, that might be, but there might be other universes. Some modern physicists like to speculate about universes beyond ours, and in some circles these rather fanciful notions are even taken seriously. I think they should be taken with a grain of salt, but that's my opinion. In any case, it seems reasonably clear that perhaps the structure or the possible structure of something like this might be related or linked to the physical world. There are other people who take a different position and say, well, no, the mathematical world is completely separate from the physical world. And even if the physical world is finite, then it doesn't matter. This sequence is still going on forever. I'm not such a fan of that point of view. I happen to think that the mathematical and the physical worlds are intimately connected. And if the physical world is finite in some strong sense, then probably the mathematical world is finite in certain sense as well. It's just my rough intuition. In any case, it seems sort of almost metaphysical or philosophical, and we should admit that, right? We should admit that when we're talking about questions like this, it's on the borderline of philosophy or metaphysics or something, or religion perhaps even. But aside from these sort of philosophical or cosmological aspects, there's more mundane issues surrounding a sequence like 1, 2, 3, 4, 5. Namely that in practice, we only have a finite amount of memory, a finite amount of time, a finite amount of energy, a finite amount of patience. So even though theoretically there might be, an infinite amount of these things available in principle, in practice the story is quite different. So in practice, as you keep going in this sequence, inevitably, no matter how powerful your computing devices are, you will eventually have to start slowing down. The size of the numbers will slowly overwhelm you, and eventually you will grind to a halt. And there's not much you can do about that. You can extend the range a little bit by increasing your computing power, but that just means that you're going to grind to a halt a little bit later. And this links, I think, to the ancient, revered approach to something like the integers, that it's actually a sequence that goes beyond our view, and that extends always beyond us, and that it's not really for us to say what the whole thing amounts to. We are not in a position, as I've mentioned quite a few times before, to grab the whole sequence and talk about the whole sequence. It always goes beyond our view. We're only capable of looking at, absorbing, understanding a finite section of it at any given time. That's just the reality of the world in which we live in, and we should be cognizant of that reality and not avoid our eyes to it. This discussion, a very important discussion, between the differences between finite things and infinite things is made cloudy by the grammatical aspect of the words in English. In English, the word finite and infinite are pretty close to each other. We're just adding this little prefix in front of the finite to make infinite, suggesting that we're just negating or taking the opposite of the meaning. So the grammar is suggesting to us that these words are somehow opposite, and in fact in practice that's often used. Okay? But I want to emphasize very, very strongly that these words are not opposites. They are actually on quite different levels of sophistication, of difficulty. Okay? They are not at the same level. And here's some other examples to try to illustrate that idea. So on the left-hand side here I have a phrase which has a pretty clear, regular meaning that we can all more or less understand. And over here is some kind of flip side where we just stick a little prefix in front of the word to sort of negate its meaning. But the point is that by doing this we get a concept on this side which is a completely different level from the one on this side. So we're going from reality over here to fiction or poetry over here. So we're talking about finite sequence to infinite sequence, but suppose we talk about a visible person. Okay, I'm visible, you're visible, and so on. What about an invisible person? Is that a concept? I don't know. I don't know any invisible people. Probably you don't either. Just by putting this little I in front of the word doesn't create a valid new concept, at least in my opinion. Mortal cat, immortal cat. What's an immortal cat? I don't know. A terrestrial fish? Okay, I think we can understand what that is. It's a fish that swims in one of the oceans or lakes here on planet Earth. What's an extraterrestrial fish? A fish that swims on some ocean on some other planet. Maybe. A breakable wall? Yeah, this wall is breakable. How about an unbreakable wall? Are there such things as unbreakable walls? I don't think so, but I could be wrong. Maybe on the side of the universe there's an unbreakable wall that simply cannot be broken. Stoppable mouse. Well, most mice are probably stoppable in one way or the other. But what about the concept of an unstoppable mouse? Like Mighty Mouse. Maybe Mighty Mouse is unstoppable. But the concept seems to be sort of off in, in Never Never Land. And this is the way I want you to think about this difference here too. All right, going from finite sequence to infinite sequence. We are changing ballparks completely. We cannot expect that the logical structures and reasonings valid for finite sequences extend to so-called infinite sequences, even if we were able to say what those things really were. So as you can see, I'm not a big fan of this word infinite in mathematics. I think it's a misused word, and it brings a lot of confusion into modern mathematics. So I think when we can, we should try to look for alternate terminology. And so I'm going to propose that what we currently talk about as an infinite sequence, we might introduce another phrase, which I'm going to call an on sequence. And that's short for the term ongoing sequence, which to me more accurately and honestly reflects the essential nature of these so-called infinite sequences. Namely, that they're ongoing, that they keep on going. At any stage, we can comprehend a finite amount, and we can watch the sequence increment and tick over. So that's what's happening. That's all there is. We can look at a certain finite amount of it, and we can see that it's continuing. It's ongoing. So that's what it is to me. It's an ongoing sequence. It's not necessarily infinite because I don't want to make metaphysical assumptions about the end of time or the finiteness or otherwise of the universe. Okay? So to me, this is a more sensible, down-to-earth, a solid way of thinking. So, of course, the question is still, what do we mean by an on sequence? What is the actual definition of such a thing? And that's going to be still a very, very hard question. That's still going to be a question that we're going to be able to answer only in stages. You might be disappointed that I'm not going to end this lecture by telling you what an on sequence actually is. It's a very, very difficult thing to do this in one blow. In fact, it's impossible as far as I'm concerned. But nevertheless, we should have as a motivator that the sequences that are appearing in Sloan's encyclopedia, those, at least most of them, should qualify as on sequences. So let's have a look at some of these sequences and see what happens with them. So after the sequence, or on sequence, of natural numbers, the next most studied and fascinating sequence is no doubt the sequence of prime numbers, which is a 40 in Sloan's list. And I guess the first fact there, the crucial fact, is the one that was known to the ancient Greeks. So back to Euclid, that this sequence really is an on sequence, that it's not a finite sequence. And these days we would say that this is an infinite sequence, but Euclid said it in a rather different way, and it's very instructive to see how Euclid phrased the theorem. He said, there are more primes than found in any finite list of primes. And by that he meant that if you have any finite list of primes, then there's at least one other prime which is not in your list. Okay? So there are more primes than found in any finite list of primes. The modern mathematician might say, well, that means that there's an infinite number of primes. But the ancient Greeks were more careful than a lot of modern mathematicians, as I've pointed out. Okay? The ancient Greeks were actually quite rigorous. They were concerned about logical clarity and purity. They didn't necessarily get everything right, but they were concerned about it. And this is, I think, a really good reflection of that concern, the way this is stated. So here's basically Euclid's proof. Suppose the primes in the finite list that you got are P1, P2, up to P little n. So someone says, here is a list of primes. There they are. How are you going to show that there's a prime that's not in the list? Euclid says, take this number, let's call it capital N, obtained by multiplying all the primes in the list together. P1 times P2 times P3 all the way up to P little n. And adding 1. So that's the definition of n. Then this number n is either prime or not. If it is prime, then it is not in the list, because this number is clearly bigger than any of these numbers. If it is not prime, well, then it is divisible by some prime, p, because Euclid knows, he established in his book on number theory, that every number is divisible by a prime, has a prime factor. All right, so call that prime factor p. But what can this prime factor p be? It cannot be in our list, because otherwise p would divide 1. In other words, if p was one of these guys here, and p is a factor of n, then it's obviously also a factor of this number, because this number contains p somewhere inside it. And that would mean that it's a factor of the difference between these two, which is the number 1. In other words, p would divide 1. But that's not possible because p is a prime. So either way, we get a new prime. Either n itself is a prime, or it has a prime factor, p, which is not on that list. Very beautiful classical proof that shows that given any finite list of primes, there is a prime not on that list. And that's our justification for thinking, saying that this is an on sequence, that we can always find a next prime. And now I want to raise perhaps a rather mischievous question. I want to ask the question, does this proof really work? This is a course in the foundations of mathematics, and it's our job to look carefully at arguments and to look at all aspects of them and think, well, are there any holes here? Are there any gaps? Are there any little weaknesses where maybe some assumptions are occurring that aren't completely clear and obvious? Well, let's think a little bit about prime numbers. Okay, currently in the year 2012, this is the largest known prime number. It's called a Mersenne prime. It's 2 to the 4311269 minus 1. That number is known to be prime. And in fact, that's been the largest known prime for 4 years now. So finding large primes is not at all easy. It takes many millions of computer hours to find a prime like this and to check that it's a prime. It has around 12 million digits, this number, if you wrote it out in Hindu-Arabic form. So this suggests something, right? It suggests that, well, okay, finding primes is not so easy. So people have been looking very hard for a bigger prime than this. Euclid's theorem says that there is a bigger prime. Why can't we find it? Why can't we just go through the motions of the proof and find the next prime? Or find a bigger prime at least? Well, there in fact are some hidden assumptions in the proof. Subtle assumptions that you might think are not worth worrying about, but they're worth pointing out in any case. The first assumption is that we can actually calculate this number. So what's the problem? Well, suppose we could list all the primes up to this number p. Let's call this p. All right, so of course we do not have any idea about most of the primes between 2 and this number. So most of the primes in that range, we do not know what they are. But suppose we could. Suppose we worked for a few thousand years and we made a list of all the prime numbers from 2, 3, 5, all the way up to this number p. Okay, and then we started to mimic Euclid's proof. So we want to compute this number. We need to take the product of all these primes and add 1. That's how we're going to find a new prime. Are we able to do that? Well, the answer is almost certainly no. This number is going to be too big for us to compute in any meaningful way. It's going to overwhelm us. And if we can't compute it, then does the proof really work? The proof required us examining this number, but if we can't compute this number, can we even say that it exists? Okay, some kind of maybe metaphysical question. But at least there's some kind of possible difficulty here in the computational aspect of coming up with this capital N number. And there's also a second assumption. Once we cooked up this number, capital N, we said, well, either it's prime or it's not. So if it's not prime itself, then we have to factor it and find a prime factor. How do we do that? Can we in fact do that? If this number is stupendously large, how do we factor it? Yes, the fundamental theorem of arithmetic, which we will talk about at some point in this course, asserts that we can do this, but is it really true? Given a number that's that big, can we in fact really factor it into prime factors? We're going to see a little bit later that that's also a questionable issue. All right, so let's leave philosophical or semi-philosophical things aside and go to our next sequence, which is very concrete and down to earth. It's sequence A000108, the Catalan numbers. And here are the first ones: 1, 1, 2, 5, 14, 42, 132, 429, 1430, 4862, 16,796, 58,786, 208,012, 742,900, and 2,674,440, and so on. I haven't specified the sequence yet, have I? Because the and so on leaves a big question mark in your minds. You don't know how the sequence goes unless you already recognize this sequence. And this is a key difference between finite and infinite sequences, that the infinite sequences cannot be specified by listing all the elements. We have to give some kind of rule or explanation of where this sequence is coming from. The remarkable thing about this particular one is that there are so many seemingly different and interesting ways of defining or describing this sequence. Perhaps the simplest is this formula. It's what you get when you take the binomial coefficient 2n choose n and divide it by n plus 1. So in terms of factorials, it's 2n factorial divided by n plus 1 factorial times n factorial. And the n can go from 0, 1, 2, and that's actually the 0th one, and that's the first one. So our indexing in this case starts from 0. I remind you that 0 factorial is 1 by definition. Okay, there's a lot of other ways of describing this. Another interesting interpretation is that it's the number of ways of inserting n pairs of brackets in a word of n plus 1 letters. So for example, if n is equal to 3, then C3 equals 5, 0, 1, 2, 3, right there. And that 5 corresponds to the 5 different ways of bracketing 4 objects into pairs successively. So Here's AB bracketed, CD bracket, all bracketed. Or you could bracket the AB and then that with C and then that with D. Or you could bracket the BC and then that with A and then that with D. Or the BC and then that with D and then that with A. Or the CD on that side with the B and then with the A. Another definition of Cn is that it's the number of walks with n left and n right steps which never move left of the starting point. So for example, if n is equal to 3, we're interested, say, in a fellow who starts here and takes a total of 3 steps to the left and 3 steps to the right in various orders, so that at the end he's back to where he started, because he's taken 3 left steps and 3 right steps, so we know he's back to where he started. But at no point has he ever moved left of his starting point. We might imagine that he's at the edge of a cliff, and if he moves left by 1 step, well, then that's game over for him. So those walks are not allowed. How many other walks can he make? Here's an example of a walk he can make. This would be right, right, left, right, left, left, represented by this little pattern here. Okay? So that's one walk that he can take, an admissible walk consisting of 3 lefts and 3 rights that get him back to where he started and which don't allow him to fall off the cliff. And if you count how many there are, you should find that there are 5 such. It's a good exercise for you to check that. Another interpretation of the Catalan numbers, which goes back to Euler, is that it's the number of triangular subdivisions of a convex n plus 2 gon. So sticking with n equals 3 again, if n is 3, then the n plus 2 is a 5 gon, or a pentagon. So here's a pentagon. And here are the 5 ways of dividing a pentagon into triangles by lines from one vertex to another. Here it's all rather symmetrical, and it's sort of obvious that these are the only ones. As a little exercise, you can try it with hexagons and show that the number of triangular subdivisions of a hexagon is 14, which is the 4th Catalan number. This might suggest that these numbers should really be called Euler numbers, but if we called everything that Euler discovered after him, then half of everything would be named after Euler. It would be very confusing. But in fact, it's a little bit interesting that on the internet one finds that there was a Mongolian mathematician who discovered these Catalan numbers some years prior to Euler. And I'm not that familiar with how he discovered them and what the context was, but that seems like an interesting development. Now, there are many more interesting combinatorial descriptions or definitions of the Catalan numbers. But there are also some different kinds of ways of approaching that sequence, and one is through a recursive definition. That's going to be an important idea for us. So the idea of a recursive definition is where you specify, say, the first term in the sequence, in this case 1, and then you specify some rule that allows you to generate next ones from previous ones. In this case, the rule is this one here, which harks back to polynumber multiplication. It's that Cn plus 1 equals C0 Cn, so the product of C0 with Cn, plus the product of C1 with Cn minus 1, and so on all the way up to the product of Cn with C0. So what's happening here is we're taking pairs, starting with 0 and n, and then we're increasing this one and decreasing this one. And then the next stage, increasing this one, decreasing this one, and so on until the final stage where we have n here and 0 here. We take all those products and add them together, and that is Cn plus 1. So, for example, let's say we've already computed C0 equals 1, C1 is 1, C2 equals 2, C3 equals 5, and you can check that these numbers satisfy this rule. Then to get the next one, C4, this would be the rule. We would take C0 times C3 plus C1 times C2 plus C2 times C1 plus C3 times C0. And that amounts to 1 times 5 plus 1 times 2 plus 2 times 1 plus 5 times 1 for a total of 14, and that's the fourth Catalan number. Now this kind of recursive definition, that might just be one of many. In fact, there's other kinds of recursive definitions of the Catalan numbers, including this sort of determinantal recursive definition, which is also pretty interesting. So if you take a determinant which is created by, on these sort of off diagonals here, sticking the various Catalan numbers. So there's the 0th one, there's the first one, and the second one, the third one, and there's the fourth one. Then that determinant of that 3 by 3 matrix turns out to be 1. And that would mean that if you didn't know this one already, but you knew that the determinant was 1, you could use that fact to compute that that had to be 14. If you go up one size, then the matrix becomes this. So there's C0, C1, C2, C3, C4, C5, and there's C6. That would give you a formula for C6. That gives you the formula for C4, C6, C2, and the even ones. If you want the odd ones, then there's a kind of a variant of that where you sort of shift everything up by 1. You sort of forget about C0 and start with C1 in making your matrix. So there's C1 along that off diagonal, C2, C3, C4, and that gives you C5. That determinant is also equal to 1. So it's kind of remarkable that these determinants have this property, but this is another way of defining, if you like, the Catalan numbers recursively. So you're getting the idea that there's a lot of different ways, potentially, of describing an on sequence. That's especially true of the Catalan sequence, which is very, very rich. But it illustrates the point that with a finite sequence, it's enough just to specify the elements. With an on sequence, we can't specify all of the elements. We can specify a finite number, but we can't specify all of them. But we need to generate a rule, or a function, or an algorithm, or any one of those other sort of strange words. But the point is, there may be a lot of different rules, a lot of different functions, a lot of different descriptions of the same on sequence, which makes pinning these things down so much more difficult than for finite sequences. So this message is important enough to repeat it, so let me just spell it out very clearly. All right. So there's a huge difference between a finite sequence, such as, say, S equals 5, 4, 3, 2, 1, finished, and an on sequence, say, such as our Catalan numbers. The former, this finite sequence, is specified by the elements of the sequence. We don't need a rule, we don't need a formula, we don't need a recursive definition. We just list the elements one by one until the end, and then we stop. And that's how we specify the sequence. Nothing more and nothing less. Anything else is secondary. However, for an infinite sequence or an on sequence, things are completely different. The latter, like the Catalan numbers, are specified by some rule or formula or recursion or algorithm or computer program with many possible equivalent descriptions. You can see why there's such a difference here, because in order to make it clear what an on sequence is, we have to tackle the meanings of these words. We have to say, well, what kinds of rules are we going to allow? What kinds of formulas are we going to allow? What kind of recursive definitions are we going to allow, and which ones aren't we? This is much more problematic when we want to be careful about things. Unfortunately, modern mathematics is not very willing to be careful about this issue. So the unwillingness to acknowledge this crucial difference is a key weakness in modern mathematics. Modern mathematics pretends that finite sequence, infinite sequence are pretty well the same thing, except that the infinite sequence just keeps on going. No, 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 okay? It is much, much, much more complicated than that. That is a vast misrepresentation of the logical structure of things. And unfortunately, that unwillingness to acknowledge this difference between finite and infinite creeps into many other disciplines in mathematics. Okay. Difference between a finite group and an infinite group. A huge difference. The difference between a finite ring and an infinite ring. A huge difference, etc., etc. Many, many different examples. We'll talk about them later. Okay, so this is a very, very important point. So we still haven't said what an on sequence is or what an infinite sequence is. I'm not in a position to tell you once and for all what an on sequence or an infinite sequence is, and I don't think anybody is. But next time we're going to start with a very modest start to try to set up a theory. We're going to start modestly by thinking about the simplest kinds of on sequences and building up our notion of on sequence slowly, slowly, carefully, one at a time. This is going to create more structure and perhaps more complexity than you might like, but hey, that's the way mathematics wants to be. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.